All right, so we're done with kind of our discussion of one-dimensional proton NMR, right? We talked about all of these different things. We talked about the information we can get from this. I thought that was like in my office. When I sit there and I'm working, then my light keeps going on, and I have to like wave over the side like this to get. Yeah. We looked at integration, chemical shifts, splitting. We talked about some decoupling experiments last time, nuclear Overhauser effect. And so today we're going to start into C13 NMR. Okay? We're not going to go that much into theory because the theory is mostly the same. You know, how signals are generated and things like that. But we will have a little intro like that. We'll talk about decoupling, coupling constants for carbons, and then we'll probably at least start talking about chemical shifts. All right? All right, this just tells us where we're at from one of those early slides. So we're doing NMR, and of course we're going to now focus on. All right, so here is a C13 NMR spectrum. This is just cholesterol. So let's just kind of look at the spectrum first and kind of highlight what we think is similar here to when we look at a proton NMR and what is different.
Same units.
Right, so we are using parts per million for the scale. So it's the delta scale, that's right. And in general, the chemical shift scale, you know, kind of, for part of it at least, mirrors what we see for proton NMR. Okay? So the chemical shift mirrors proton NMR, which means that, you know, the upfield range is going to be the aliphatic part, the methyls and methylenes and, you know, methynes, the sp3 hybridized. In the middle, we're going to have the carbons that are bonded to electronegative atoms. Then we're going to have the double bond region and the aromatic region. The difference, though, is that we can now see signals for carbons that don't have protons on them. So we'll have some extra chemical shifts to take into account that we never saw in proton NMR. Okay, so it kind of follows that. We have, what about the chemical shift range compared to proton NMR? Yeah, we have a much larger chemical shift range.
It does think I'm negative though, right?
I think for only unusual things would be negative, right?
In carbon.
Huh?
In carbon NMRs.
Yeah, and in proton, right? So the places that we would tend to see negative chemical shifts is if we have a very electropositive group attached to a carbon, so it's pushing electron density back on the carbon. So TMS is still at 0, so it's more like, you know, methyl, you know, alkyl metal compounds, you know, alkyl lithiums or something like that, you know, where you have a plus on the metal and pushing electron density under the carbon. That would cause a situation where it's very shielded, right? Larger delta range. All right. In this spectrum, at least, notice that all the signals are singlets. The other thing that maybe we can't really notice from this spectrum, and they're actually, most of these signals are kind of similar intensities, but the way that we normally run C13 NMR, the area under the carbon signal is not proportional to the number of carbons. So we can't integrate the normal C13 spectrum. Okay, so peak areas not proportional to the number of carbons. Okay? It's not to say we can't run an experiment that allows us to do that, but that's not how we usually do this. Okay, so let's talk just a little bit about the theory. We already know that C13 NMR is reasonably insensitive, right? So what was the reason for that? Just the abundance, right? It's only 1 point natural abundance. But that's not the only reason. Okay, so remember that the energy gap, delta H, which is also related to, here, what's going on? H nu, which is also related to the frequency, equals this value here, this gamma H B0 over 2 pi. Remember, H is just Planck's constant, B0 is the applied magnetic field, but this is where this gamma value, this magnetogyric ratio comes in. And notice right here, here's two values for this gamma value for protons and for C13. And notice that this proton value is roughly about 4 times bigger than the carbon gamma value. Okay, so this is about a 4-to-1 ratio. So because C13 has a smaller magnetogyric ratio, it also means that the energy gap between the different spins is smaller. And remember, what we're really detecting is just the excess number of spins in the alpha state. So as the energy gap gets smaller, you know, the number of excess spins gets smaller as well. All right, there's less kind of residual signal that we can observe. All right, so this ends up making it be even less sensitive. Okay? So C13 has a smaller delta E. So it's also going to be at a different frequency range. And the frequency range is going to be roughly 1/4 of what the proton NMR frequency range is. So for a given instrument, so say if we have a 400 megahertz NMR, we call it a 400 megahertz NMR, which means that that's the proton frequency. Then the C13 frequency is only 100 megahertz. Okay, so when you report this, in fact, you in a paper, the frequency that you're running it at, you have to take this into account. So at 500 megahertz NMR downstairs, the carbon frequency is only 125. Okay? Now, the reason that we have all of the peaks coming out as singlets is because we typically run these with what's called broadband decoupling. And there are a number of approaches to doing this, but in general what happens is this is the same kind of decoupling experiment that we did selectively for protons, right? Irradiate one proton and remove the coupling on its coupling partner, right? It collapses the signal. But in this case, what we're going to do is we're going to irradiate all of the protons in the molecule and remove the coupling to the carbons. That's what makes the carbons all show up as singlets. Okay, so this removes the proton C13 coupling, right? Because since we know that proton and C13 are NMR active, then we should see the coupling there. So so as a little side thing here then, why don't we see the proton C13 coupling when we look at a proton NMR spectrum?
Because there's not a lot of carbon.
Right, because
The frequency that we're running at, or the scans we're running at it, we wouldn't be able to register the H to 13.
well, what would it look like if we saw C13 coupling between the protons and the C13?
HSBC or HMBC.
That's a 2D, that's a 2D NMR.
Oh, okay.
Well, even in 1D.
Yeah, he was thinking about the 2D.
Oh, okay.
I thought
Okay.
you would see a 2D spectrum. Sorry, never mind.
Well, we can do that.
Yeah,
We will talk about that.
You're referring to like just the one.
Just when we look at a proton NMR spectrum, why don't we see coupling to the
Is
carbons?
it too small to see?
Yeah, basically because it's only 1.1% of the carbons are NMR active.
You can see satellites.
Is it the satellite?
Yeah,
Is it
so
the satellite?
exactly. So if you have a
That's what the satellite is?
Yeah.
if you have a singlet like this, and it's hard to see these unless it's kind of away from everything else, right? And the spectrum is not noisy or anything. But down here, you can oftentimes see a pair of satellites like this. And what those are called the C13 satellites. And in fact, if we measure this gap, and you got to make sure that, and my drawing is not quite right, but they should be symmetrically centered around the proton signal. Okay? And so this distance right here would be the one bond carbon hydrogen coupling constant. Okay, and we'll talk about that coupling constant more in a minute.
Yeah, we see that a lot.
Mm-hmm.
Yeah.
Oh, you do? Okay.
Yeah, we
Every
see it
now and then.
constantly.
Okay.
In one of our lake hunts we make.
Yeah, right.
Because it's so clean that when you zoom in just a little bit, you see the satellites. And
Yeah. So those should be essentially at 1.1%, but of course, because it's a doublet, it's going to only be half of that for each one, right? Okay, so we can run C13 as a coupled spectrum. So here's a comparison. These are both of cholesterol. Notice that, some carbons, like right here, when we go to the coupled one, this is coupled up here, it remains as a singlet. Right? So that essentially tells us that that's a quaternary carbon. There's no hydrogens attached.
So that's the proton on top, just to make sure, right?
The S?
No, just the spectrum on top.
No, that's the coupled C13 spectrum.
Oh, okay. Just want to make sure.
Yeah,
So a coupled T13 spectrum, it doesn't have to be 2D. It can be.
right. We
Okay.
just don't do this proton decoupling. So we essentially run it just like a proton spectrum, right? We don't do any extra decoupling or anything.
Does it take longer than a normal carbon?
Yes.
The coupled takes longer than a decoupled?
Yeah, so for I'll tell you about some different reasons in a minute, but one reason is that if you take any singlet and you split it into a doublet or a quartet or a triplet, then it essentially gets smaller, and it can get closer into the signal to noise, right? Unless you have really good signal to noise, it reduces the peak heights if we're splitting it up. But so, for example, this one, we notice that this peak is now a doublet, and that means that it's a CH. It has one proton attached. We're just looking at just the one bond couplings here. Right? Here's another one that shifts to a doublet. A lot of these are, right? Here's two peaks that are each going to a doublet. But over here, notice that this signal here goes to a quartet. So that's a methyl group. Right, so this information in here, look at this one right here. Right there, that looks like a triplet. Right, so it can tell us immediately how many protons are bonded to those carbons. Right, the difficulty is we have less signal to noise, and then just look at how complicated this gets when all of these carbon multiplets start overlapping on each other. Okay, so you get much better resolution when we have them all as singlets. And we have better ways to do this now anyway. Okay, so,
A couple C13.
no, there's much better ways to do this. Yeah. But we should know that that it's there, and that a lot of the other experiments that we're going to look at depend upon this coupling.
That is really helpful to mention anymore.
All right, so let's just look at a basic C13 experiment. Okay, so we'll draw out kind of the pulse sequence. The pulse sequence on C13 is just going to look like the proton pulse sequence, right? So we're gonna do this in the frequency range of the carbons instead of the protons, right? So we're just gonna start out here. We're gonna have this relaxation delay, right? So this is just like we did before. We're gonna give it a pulse, and then we're gonna do acquisition, right? So this is our pulse, and this is acquisition, right? And then we can do another delay, another pulse, and then acquisition, right? So it's just like before, and we just repeat these, add them up as many times as we need to get the required signal to noise. All right, so in addition to this, though, we also have another channel which is for the protons. And in the kind of the simplest variation of this, essentially for the protons, what we do is we just turn on the decoupler and we just leave it on. So we just say that the decoupler is on. So we're irradiating the whole proton range the entire time that we're recording the C13 spectrum. Okay?
You'd be irradiating at 100 megahertz for the
C13,
but always.
and also at 400 megahertz the whole time to cause decoupling between the protons and the C13s. Okay?
So it's like there's two radio waves.
Yes. Yeah. And so this gives us a decoupled spectrum. All right, so that's the main thing, but there's some kind of side things that result from this as well. Another thing is that there is some nuclear Overhauser effect that's going on. So when we irradiate the protons, some of the signal energy we put into the protons gets transferred to the carbons, and it enhances the carbon signal. All right, just like when we saw the proton-proton NOE. And so this is essentially created during the relaxation delay, and that causes oftentimes the protonated carbons to be bigger because they're enhanced by NOE than the quaternary carbons. So there's more, the more protons there are on a carbon, the more NOE there is. Okay? So,
And that happens, you said that happens during the acquisition or during?
no, that happens during the pre-acquisition
Okay,
delay.
Just want to make sure,
Yeah. So by keeping so really the decoupling only takes place during the acquisition. When we have the decoupler on during the acquisition, that's when decoupling happens. When we have the decoupler on during the relaxation delay, that's when the NOE builds up. Okay? So the protonated carbons are enhanced. Okay? So, this is one reason why we can't directly integrate the carbon signals. Okay? One, though, is, the first one I've got here, is that the relaxation rates for different carbons have a very wide range. Okay? So, the T1 relaxation is very different. Let's say for quaternary carbons versus something like a methyl group. Okay, because the T1 mechanism is passing energy off to other atoms in the surrounding molecule or in the solution even. So the more protons there are directly attached, the faster the relaxation is. All right, so if we don't allow the relaxation delay to be long enough, then some of the carbons, especially the quaternary carbons and the carbons that don't have very many hydrogens, will not fully relax to their equilibrium state. Okay, and because of that, we start to lose signal intensity. All right, so if this relaxation delay is not long enough, we're going to lose some signal intensity. Okay, and in essence, really I didn't write down some values, but to make the relaxation delay long enough, we may be waiting, 5, 10 seconds or something between scans. And so it's a very slow process then. All right, so the other reason here is what I already mentioned, is this nuclear Overhauser effect, and this involves signal transferred from the protons to the C13. So it enhances that signal, and so usually it's greatest the more hydrogens we have attached. So we get more NOE for a CH3 than we do for a CH2, for a CH, for a quaternary carbon. All right, and this is, for these reasons, this is why we oftentimes see in C13 NMR that the quaternary carbons are often very small. Okay, their intensities are small. All right, so we can run C13 experiments to either allow us to integrate or things like that. So I'm going to show you two different ways. Okay, the first one is going to be called the inverse gated decoupling. Okay, so in this case, the proton channel, let's do the C13 first. The C13 channel is always going to be the same. And this is just going to be the normal pulse sequence. Okay, so we got our relaxation delay, we give it our pulse, we have acquisition. Right? We have our delay, we have our pulse, and acquisition. Right? And we're just repeating this. Okay, on the proton channel, though, in inverse decoupling, what we do is we turn the decoupler off during the pre-acquisition delay, but we turn it on during acquisition. So this is on this is off. We turn it on during acquisition and then back off. Okay, so we're gating it on and off. And what this gives us is, in this case, because we have it off during the pre-acquisition delay, we have no NOE that's built up. Okay, because it's during the pre-acquisition when we build up NOE. All right? What about coupled versus decoupled? Is the C13 spectrum going to be coupled or decoupled?
Decoupled.
Decoupled, because we have the decoupler on during acquisition.
So all you're gonna lose is the NOE, but still have the decoupling.
Right.
If you did it opposite, you would have couple.
Yeah, that's the next one we're going to draw out. Yep, exactly. All right, so with this one, if the relaxation delay is long enough, so if we make this very long, 5 times whatever the T1 values are for the slowest relaxing carbons, is long enough, then we can integrate. Okay, because we've removed the NOE and we've removed the problems with the different relaxation rates because we've waited long enough. But, of course, this is going to be, well, it's decoupled, but we lost NOE, so it's, we've reduced sensitivity because there's no NOE, but we're still decoupling, so it's into single signals at least. All right, so the reverse of this is called the gated decoupling. All right, and so the C13 is just the same. Okay, the difference is in the proton NMR, and what we're going to do this time is we're going to turn the decoupler on during the pre-acquisition and turn it off during, no, pre-acquisition, turn it off during acquisition. So we're going to do just the opposite thing. So this is on and off. Okay, so this one is going to give us NOE, right, because we have it turned on during the delay. What about coupling or decoupling? This would give us a coupled spectrum. Okay, coupled with NOE. All right, so there's just various ways that we can do this. I think there's better ways to do most of these things nowadays, but just so we know what's going on. So if we compared some different spectra run under these different conditions, we could see differences in the signal intensities. All right, so the top one example here is the inverse gated with a long relaxation delay. And notice that the signal intensities are the same, right? So it's one, we could integrate this if we wanted to.
That's all that is.
Huh? Yeah,
That's chloroform.
this is chloroform.
Deuterium has a different spin.
Right, so deuterium, remember, so deuterium is a spin 1 nucleus. And so instead of just plus 1/2 and minus 1/2 that we see for spin 1/2 species, deuterium with spin 1 has a -1, 0, and 1. So there's 3 different possibilities for the spin. And so when it couples to other nuclei, it splits it into 3 peaks. Okay, so this one could be integrated. Okay, here's the inverse gated, but with a shorter relaxation delay. And notice that these, I guess these are integration numbers here. Here, 0.35 and 0.41. The quaternary carbons, these are both quaternary, are getting much smaller. Okay? And then, if we just have a normal, I think it's just a normal C13, normal decoupling, with a relaxation delay that's short, then look at these quaternary carbons are really small. Okay? So this is both a combination of not allowing those carbons to relax completely, and that those carbons are not benefiting from any NOE from attached protons as well. Okay, so these are all spectra of just this diethyl phthalate. So we have this, that we've got the carbonyl out here at almost 170 for the ester. We have the quaternary carbon where on the benzene ring where the 2 esters are attached, and then we have the other 2 carbons because we have this plane of symmetry down the middle, right? And then the ethyl group. All right? Okay. The actual coupling constants. I may have doubled that one. At least it was in my other one. All right, so first we're going to look at the 1 bond coupling constant. Okay, so we didn't look at this in proton NMR, right? Because we don't have a proton 1 bond coupling constant. All right, so as a general range, we can use this equation right here, which says that the 1 bond coupling constant will equal to 500 hertz times the percentage of S character in the hybridized orbital. Okay, so for example, if we were looking at a sp3 hybridized carbon, we would say that the 1 bond CH coupling equals 500 times the percent of S. So it's only 25%, right? Oops, that's not a... by 25%, and so this comes out to 125 hertz. All right, so how does this coupling constant compare to what we saw for proton-proton couplings? It's big, right? Because the biggest coupling constants we saw for protons in proton-proton was maybe nearing 20 at the most, right? Usually the biggest for trans is maybe 17, and so these are well over 100. Okay, if we were doing a sp2, right, it would be 500 times, 33%. So it comes out to about 166 hertz. Okay, so as we get more S character, the coupling constants become bigger, right? The bonds become stronger too. So here's this table's kind of small, but so 125 is exactly what they have here for methane. Okay, and notice as we go down in this direction, one thing that changes in this region is that we're going into smaller rings for one thing, and as the ring size gets carbon-carbon ring size gets smaller, the coupling constant gets bigger. Right? So I think that's because as the carbon-carbon-carbon angle gets smaller, the carbon-hydrogen gets bigger. And so it's basically a different hybridization. So as the carbon-hydrogen, as this angle widens, then we're essentially adding more S character. Or the other way, the carbon-carbon-carbon bond, as it gets narrower from 109.5, which is the perfect sp3, down to, whatever for cyclopentane, 118 to 90 for cyclobutane, that one is getting more and more p character because p orbitals are at 90-degree angles to one another. So the p character is increasing in the carbon bonds, but the carbon-hydrogen bonds are opening up, and so they're getting more S character. Right? So as we get more S character, just like the equation shows up here, the coupling constant gets bigger. All right, so, but we can see for kind of sp3, we would call them, it can be anywhere from 125 up to, well, cyclopropanes are up near 200. They're up over the normal coupling constant for sp2. Right, if we have double bonds, then these are starting at around 150 and getting bigger. Here's triple bonds. sp is up in the 200s. Okay? So we have general ranges based upon hybridization. Substitution can also influence the one-bond coupling constant. So, for example, here's some applications, and these were always better applications when there were people from Dr. Chang's group.
Yeah, I think number 6 would have really been their.
It's hard not to go to modern.
Yeah, right. Well, they've all been through here.
Yeah.
So, for example, if we had these two, if these were sugars and we had two different anomers, so the alcohol on the anomeric position is either beta versus alpha, the size of the coupling, the one bond coupling constant for the proton changes. So it's a little bit lower if that carbon-hydrogen bond is axial than if it's equatorial. Okay, so if you could directly, and this is a case where you might be able to, if that anomeric proton is well separated from other protons in the proton spectrum, you might be able to just blow it up, look for the C13 satellites, and measure the coupling constant and determine the stereochemistry. Right? So it's a kind of a direct way to do that. Another example, when I was a postdoc down at University of Utah, this compound here was isolated from a marine invertebrate. And so structure was determined to have this thiomethyl group here, but it wasn't really clear during the structure determination whether that methyl group was either directly attached to the aromatic rings or tell the difference between the methoxy group. And so it turns out that the one bond coupling in that methyl group is different depending on if it's this thiomethyl or if it's a methyl directly attached to a benzene ring. In these two cases, the chemical shift would be pretty similar, but the coupling constant is quite different. And then the methoxy group was even different again. And so it just gives you more structural information to know that that value can change. And I think, for me, in some ways, it's interesting when you can, to just look at like in the top example, just look at this one coupling constant and be able to tell that stereochemistry is kind of a very, surgical way to answer a question. You're not blasting it with a shotgun and getting all possible data and then only looking at one piece of the spectrum. All right, so we can also sometimes see two bond couplings in the graph there. It's kind of hard to see. But in general, I think the two bond couplings are usually pretty small. Well, much smaller than the one bond for sure. And what are these from? So, well, these are like 4 to 6. These are, the 1 to 5 ranges. The aldehydes look like they're an unusual case. And then they're bigger in the alkynes as well. But here's a couple of examples. So if we look at these systems where we look at this proton in this Newman projection to the carbon, so this is more of another, application if we had, carbon chains with alcohols on them. If, and here's the OH or ether, if that's an anti-arrangement, then the coupling constant is positive. If these two are gauche, we're still looking at just the coupling from the hydrogen in red to the carbon in red, then it's a negative value. And one place, an example here, before we looked at the one bond coupling, but if we look at the coupling from this proton to this carbon, these are anti, like above, and so it's a positive value, only 1 hertz, but positive. Here, these two are gauche. We're still looking at the one bond coupling, and it's a negative value. Okay, so it again gives us some additional information. This is the same thing, I think, right there. So it's just another possible. Three bond couplings, so this is more like a vicinal coupling, also follow kind of this, remember this Karplus relationship that we saw for vicinal proton couplings, right, where the size of the coupling constant depends upon the dihedral angle, and it was the biggest when they were next biggest when they were syn, when they were on the same plane, and went to near 0 if they're 90 degrees. Okay, so the same type of relationship follows for this 3 bond coupling. And so usually the 3 bond couplings are a little bit bigger than the 2 bond couplings, but notice that 9 hertz when they're anti, 6 when they're gauche, or maybe they're supposed to be, yeah, they're probably eclipsed. And then around 0 when they happen to be a 90-degree angle. Another place that this can come in is if we have protons on sp2 hybridized carbons. So let's see, what do we have here? So it's from A to this carbon, this coupling. If those are cis, then it's 7.6 hertz, and if they're trans, then it's bigger, 12.6. So again, kind of the trans coupling is bigger than the cis. And if we have 3 bond couplings around a benzene ring, or couplings around here, notice that the 1 bond coupling is 159. So these are all couplings to that red carbon. If they're ortho, from B to that carbon, 1.1 to 4. If they're 3 bond, it's bigger, 7 to 10. And when it's 4 bond, then it's negative, but it's small again. And so these differences in coupling constants are what can be taken advantage of if you want to do 2-dimensional heteronuclear experiments. You want to look at protons between carbons and protons, and you want to optimize for a certain number of bonds. So you can say run an experiment that optimizes for the 1 bond coupling, because the 1 bond coupling is so much different than the 2 or 3 or 4 bond couplings. Or you can run an experiment that optimizes for the 3 bond coupling, because that, again, is slightly different from the 2 bond or the 4 bond couplings. So you take advantage of these different sizes of coupling constants. Okay, so the 3-bond couplings are especially good for things like this when we look at two-dimensional. If we want to see coupling between a carbon there with another carbon over here, and let's say that this carbon here is a quaternary carbon, then if we're just looking at proton couplings, we can't see past that quaternary carbon because there's no protons on it. But if we can use this 3-bond coupling, then we can see past the quaternary carbon. Or if we have a situation where we have something like an oxygen or some heteroatom in there, again, it has no protons on it, so we can't just look at proton couplings, but we can see past the heteroatom and see that coupling and link those pieces together. So this becomes useful. All right, so let's look at chemical shift then. All right, so in general, chemical shift, again, follows hybridization. All right, so, well, these are kind of overlapping ranges, though. So sp3 could go all the way from minus 20 parts per million to 100 parts per million. And usually 100 parts per million, the kind of thing would be a carbon that maybe has 2 oxygens attached or something, would be around 100. The sp2 hybridized, so either on a carbon-carbon double bond, a benzene ring, or a carbonyl, can be from 120 up to 240. And then, like we saw in proton NMR, the alkyne, the sp hybridized carbons are in kind of a different, unique range in the middle. If we look at the sp3 and we add electronegative groups, they cause de-shielding, just like in proton NMR. Right? So methane itself is at minus 2.3. We add an amine, it goes to almost 27. We add an oxygen to 49, to fluorine to 75. So we just adding more electronegative groups. Those groups pull electron density away from the carbon, causing de-shielding. Okay, so this is the same kind of trend that we saw before. We can also use resonance to help us understand differences in chemical shift. Okay, for example, if this X group here was electron withdrawing, then it might pull electron density out this way, which is going to give us resonance that looks like this. Let's just write it, whatever that X group is, with a plus over here, right? And then that could go around further. And so what we end up with electron withdrawing groups is we have a delta plus here, a delta plus here, and a delta plus here, right? And when we add those delta plus groups, what's that going to do to the chemical shift? Right, it's going to cause more de-shielding, more downfield. So as an example, we could look at that benzonitrile over there. So a nitrile is an electron withdrawing group, and the nitrile carbon itself is at 119. And then if we look at the ring, there's not a huge difference here. 132.2, 129.2, 132.8. So those two, ortho and para, are slightly more downfield than the meta. And in fact, let's see, I guess it's this one is only at 112. Is that where it's attached? All right, if we have electron donating groups, it's just the opposite. You know, we've kind of talked about this a little bit. Well, we talked about it in terms of proton NMR. So this is electron donating. Then the resonance is typically going in the opposite direction. Right, so we end up with a delta minus here, delta minus here, delta minus over here. Right? So when we build up electron density, then that causes more shielding. So like aniline up above, this carbon is at the 116.1, meta is 129.8, and para is 119.0. When we look at the position of direct attachment of the nitrogen, though, because that nitrogen is more electronegative, right, it's going to cause a downfield shift. So this is at about 147.7. All right. So general trends. So these same type of trends play a role in carbonyl chemical shifts. Right? So when we look at a carbonyl group, the type of resonance we think about is having the oxygen pull the electrons up onto it, giving us a resonance structure with a minus on the oxygen and a plus on the carbon. All right, so if we look at kind of the, like a ketone or an aldehyde like this, we have this resonance and we don't have anything to offset it, so the ketone is at 206.7, the aldehyde is somewhere greater than 190. However, if instead of just having a carbon or hydrogen there, we have some X group that has non-bonding electrons, when we do this same resonance, then this X group can donate electrons to kind of reduce the delta plus on the carbon. All right, so we end up with another resonance, which is like this. Like this. All right, so if we look at like an ester, then this is at 171.3. Right, so it's much upfield from where the ketones and aldehydes are. And if we look at an amide, it's the same kind of thing, 173.4. Okay, so in general, if we have ketones and aldehydes, these are usually from maybe 190 up to maybe 220. If we have esters, amides, carboxylic acids, these are all usually between about 165 up to 180. Okay, so we can tell the difference between these different types of carbonyls. And so this is a big advantage for C13 NMR, because the carbonyls we can't really see in the proton NMR, right? We've kind of implied that they're there based upon chemical shift. But in the C13, we can actually see them. All right, so conjugation also affects, so this is kind of a resonance effect. But if we looked at some double bond chemical shifts, for just this terminal alkyne, it's about 140.2 for the interior one and 112.8 for the terminal carbon. If we add another double bond and cause some conjugation here, then this goes slightly upfield, 137.2, and this is a little bit downfield, 116.2. When we add conjugation next to carbonyls, here's just an isolated aldehyde, but it goes up almost 10 parts per million when we add conjugation next to it. Again, you know, we'd have the delta plus next to the carbonyl, at the carbonyl carbon, but that pi bond can donate electron density to it. If we have a benzene ring, likewise, this is at 190.7. So for aldehydes, if it's more like 190, then it's usually conjugated to something. If it's 200 or over, it's usually not conjugated. If we look at ketones, they're a little bit further down field. This one is at 206.3. Add a double bond, 198.1. Next to a benzene ring, 195.7. So oftentimes those ketones or aldehydes, if they're in the 190s, then it means they have some conjugation next to them. All right. And the last thing here, well, almost the last, has to do with steric interactions. All right, so C13 is also depends upon crowding and things like that. So in fact, if we have a carbon that we're looking at, let's say we have this, we'll call this alpha, beta, gamma, delta. If we have these positions crowded close to each other, essentially those electrons get repulsed and the electron density gets pushed it back onto the carbons. Okay, so steric repulsion pushes electron density onto the carbons. So, examples, if, let's just make this one, I think this is what I did before. Let's put another CH3 over here so it's symmetrical in the other way as well. Okay, so 22.7 for the methyl group. This carbon here is at 32.65. This carbon over here is at 35.65. Now, if this methyl group is axial, then we get steric interactions here, and this should push electron density back on the carbons and cause upfield shifts of those carbons. Okay, so where we see the upfield shift is even at the methyl group itself is at 20.1, so that went from 22.7 to 20.1. This carbon is at 30.15 instead of 32. And this one right here, 30.6 versus 35. So in these cases, to really use some of this, you'd have to probably have two compounds to compare each other with, right? But a good place that you can use this is on cis or trans double bonds, right? We know we can look at the proton couplings, but we can also look at the C13 chemical shifts. So if this is trans, this is methyl group is at 16.5, and this CH2 is 34.1. But if we have this being cis, we get steric interactions between these two positions. This moves up to 11.4, and this is at 28.2. Okay, and so in fact, you can, let's see which ones here. You can sometimes determine stereochemistry of carbon chains just based upon the chemical shifts. So really the last thing that I think I'm going to mention today is that you can also see chemical shifts for isotope differences. And so you might see this even in the C13 NMR. If you blow up your solvent, you might see the residual signal might show up differently. So chloroform, protonated chloroform has a chemical shift of 78.0, but deuterated is 77.0. One place that you can use this, and I don't actually have any numbers for this one. I should have brought up an example that we did one time. If we, for example, had something like this, where we had a methoxy group and a phenol. Now, both of these groups have similar, influences on the chemical shifts in the benzene ring. So just by looking at the C13 NMR, it would be difficult to tell which carbon has the OH on it and which has the methoxy group. Okay, so these two, difficult to tell apart. One thing that we already talked about in a proton sense is that you could derivatize this molecule and make an ester out of that phenol, and then we would see a definite chemical shift change for the carbon bearing the ester. But a simpler way is to just do a deuterium exchange. So we could run two different spectra. One, we could say run in D3 methanol. And in this case, we would have an OH here. Right? Or we could run this in D4 methanol. And in this case, the OH, the H would exchange for deuterium. And we would have OD. And in fact, if we compare these two would have the same chemical shift. And these two would have different chemical shifts. So we could, and it's just a small difference. I don't really have a number here to tell you how much. I think it's only on the order of a part per million or something, or less. But you can see the difference. You can see one shift and not the other one. And so you could, in fact, based upon that, assign which carbon has the OH versus the methoxy group. All right. Okay, so that's basically, I think, all we'll talk about chemical shifts. So I think next time we'll be able to start working through a bunch of problems. We'll probably spend most of the day on Tuesday working problems. And then maybe I'll have another problem set for you, so you can practice that too.